Cycling of nitrogen in the ecosystem. The sources of inputs of nitrogen under natural conditions are the bacterial fixation of atmospheric nitrogen, addition of inorganic nitrogen in rain from such sources as lightning fixation and fixed, juvenile, nitrogen from volcanic activities, ammonia absorption from the atmosphere by plants and soil, and nitrogen accretion from windblown aerosols, which contain both organic and inorganic forms of nitrogen. In terrestrial ecosystems, nitrogen, largely in the form of ammonia and nitrates, is taken up by plants, which convert it into amino acids and proteins. Animals, primary macro consumers, may eat the plants and utilize the amino acids from the plant proteins in the synthesis of their own proteins and other cellular constituents. When animals and plants die, the decay bacteria convert the nitrogen of their proteins and other compounds into ammonia. Animals excrete several kinds of nitrogen-containing wastes, urea, uric acid, creatinine, and ammonia, and the decay bacteria converts these wastes to ammonia. Ammonia may be lost as gas to the atmosphere, may be acted upon by nitrifying bacteria, or may be taken up directly by plants. The nitrates may be utilized by plants, immobilized by microbes, stored in decomposing humus, or leached away. This material is carried to streams, lakes, and eventually the sea, where it is available for use in aquatic ecosystems. Their nitrogen is cycled in a similar manner, except that the large reserves contained in the soil humus are largely lacking. Life in the water contributes organic matter and dead organisms that undergo decomposition and subsequent release of ammonia and ultimately nitrates. In aquatic ecosystem, atmospheric nitrogen is fixed by numerous blue-green algae. Under natural conditions, nitrogen lost from ecosystems by denitrification, volatilization, leaching, erosion, wind-blown aerosols, and transportation out of the system is balanced by biological fixation and other sources. C. Sedimentary cycles. Mineral elements. Required by living organisms or obtained initially from inorganic sources. Available forms occur as salts dissolved in soil, water or lakes, streams, and seas. The mineral cycle varies from one element to another, but essentially it consists of two phases, the salt solution phase and the rock phase. Mineral salts come directly from the Earth's crust by weathering. The soluble salts then enter the water cycle. With water they move through the soil to streams and lakes and eventually reach the sea, where they remain indefinitely. Other salts are returned to the Earth's crust through sedimentation. They become incorporated into salt beds, silts and _electric. Discharge G atmospheric. U equals nitrogen oxide nitrogen. Fixation. Blue-green algae. Denitrifying. The nitrogen cycle. Limestones, after weathering they again enter the cycle. Plants and animals, the living components of the ecosystems, fulfill their mineral requirements from mineral solutions in their environments. Other animals acquire the bulk of their minerals from plants and animals they consume. After the death of living organisms, the minerals are returned to the soil and water through the action of the organisms and process of decay. There are different kinds of sedimentary or mineral cycles, depending on the kinds of elements, but following two cycles are very significant for an ecosystem. Sulfur cycle. Sulfur, like nitrogen, is an essential part of protein and amino acids and is characteristic of organic compounds. It exists in a number of states: elemental sulfur, S, sulfides, sulfur monoxide, sulfide and sulfates. Of these three are important in nature: elemental sulfur, sulfides and sulfates. The sulfur cycle is both sedimentary and gaseous, i.e., it includes gaseous phase and sedimentary phase. The sedimentary phase of sulfur cycle is long-term and in its sulfur is tied up inorganic and inorganic deposits. From these deposits, it is released by weathering and decomposition, and is carried to terrestrial and aquatic ecosystems in a salt solution. Atmospheric gaseous phase of sulfur cycle is less pronounced and it permits circulation on a global scale. Sulfur enters the atmosphere from several sources: the combustion of fossil fuels, volcanic eruption, the surface of the oceans and gases released by decomposition. Initially sulfur enters the atmosphere as hydrogen sulfide, HS, which quickly oxidizes into another volatile form, sulfur dioxide, SO. Atmospheric sulfur dioxide, soluble in water, is carried back to Earth in rainwater as weak sulfuric acid, HSO. Whatever its source, sulfur in a soluble form, mostly as sulfate SO7, is absorbed through plant roots, where it is incorporated into certain organic molecules, such as some amino acids e.g., cysteine and proteins. From the producers, the sulfur in amino acids is transferred to the consumer animals, with excess being excreted in the feces. Excretion and death carry sulfur in living material back to the soil into the bottoms of ponds, lakes, and seas where the organic material is acted upon by bacteria of detritus food chain. Within the detritus food chain, the sulfhydryl group CHISH of amino acids e.g., L-cysteine is separated from the rest of the molecule as hydrogen sulfide H, S by most decomposing bacteria as a normal part of the degradation of proteins. In an aerobic environment, the hydrogen sulfide is oxidized to sulfate by bacteria specially adapted to perform this conversion. H, S plus 2O, so, equals plus 2H. Photochemical. Direct utilization of life in the water contributes organic matter and dead organisms that undergo decomposition and subsequent release of ammonia and ultimately nitrates. In aquatic ecosystem, atmospheric nitrogen is fixed by numerous blue-green algae. Under natural conditions, nitrogen lost from ecosystems by denitrification, volatilization, leaching, erosion, wind-blown aerosols, and transportation out of the system is balanced by biological fixation and other sources. Both chemically and biologically, terrestrial and aquatic ecosystems constitute a dynamic equilibrium system in which a change in one phase affects the other. C. Sedimentary cycles. Mineral elements. Required by living organisms or obtained initially from inorganic sources. Available forms occur as salts dissolved in soil, water or lakes, streams, and seas. The mineral cycle varies from one element to another, but essentially it consists of two phases, the salt solution phase and the rock phase. Mineral salts come directly from the Earth's crust by weathering. The soluble salts then enter the water cycle. With water they move through the soil to streams and lakes and eventually reach the sea, where they remain indefinitely. Other salts are returned to the Earth's crust through sedimentation. They become incorporated into salt beds, silts and _electric. Discharge G atmospheric. U equals denitrifying route. I. Bacteria, nodules, Re. FS. Nitrobacter. Other. I. Sulfur cycle. Sulfur, like nitrogen, is an essential part of protein and amino acids and is characteristic of organic compounds. I. Sulfur cycle. Sulfur, like nitrogen, is an essential part of protein and amino acids and is characteristic of organic compounds. I. Sulfur cycle. Sulfur, like nitrogen, is an essential part of protein and amino acids and is characteristic of organic compounds. It exists in a number of states: elemental sulfur, S, sulfides, sulfur monoxide, sulfide and sulfates. Of these three are important in nature: elemental sulfur, sulfides and sulfates. The sulfur cycle is both sedimentary and gaseous, i.e., it includes gaseous phase and sedimentary phase. The sedimentary phase of sulfur cycle is long-term and in its sulfur is tied up in organic and inorganic deposits. From these deposits, it is released by weathering and decomposition, and is carried to terrestrial and aquatic ecosystems in a salt solution. Atmospheric gaseous phase of sulfur cycle is less pronounced and it permits circulation on a global scale. Sulfur enters the atmosphere from several sources: the combustion of fossil fuels, volcanic eruption, the surface of the oceans and gases released by decomposition. Initially sulfur enters the atmosphere as hydrogen sulfide, HS, which quickly oxidizes into another volatile form, sulfur dioxide, SO. Atmospheric sulfur dioxide, soluble in water, is carried back to Earth in rainwater as weak sulfuric acid, HSO. Whatever its source, sulfur in a soluble form, mostly as sulfate SO7, is absorbed through plant roots, where it is incorporated into certain organic molecules, such as some amino acids e.g., cysteine and proteins. From the producers the sulfur in amino acids is transferred to the consumer animals, with excess being excreted in the feces. Excretion and death carry sulfur in living material back to the soil and to the bottoms of ponds, lakes, and seas where the organic material is acted upon by bacteria of detritus food chain. Within the detritus food chain, the sulfhydryl group CHISH of amino acids e.g., L-cysteine is separated from the rest of the molecule as hydrogen sulfide H, S by most decomposing bacteria as a normal part of the degradation of proteins. In an aerobic environment, the hydrogen sulfide is oxidized to sulfate by bacteria specially adapted to perform this conversion. H, S plus 2O, SO, equals plus 2H. Photochemical. SO equals OXIOAOP. Direct utilization of atmospheric SO. Forest. Dot. Equals in 3. I grassland. Pipe closing square bracket. 1 II. 1 Ethan wastes. GR. Detritus food chain. I. B. E. G bacterial S ontane. The sulfate produced then can be reused by the autotrophs. In anaerobic environments, such as bottom of certain lakes, it is impossible to oxidize sulfide by this means, because the process of oxidation requires oxygen. But if infrared radiation is present in these environments, there are photosynthetic bacteria that can use it to manufacture carbohydrates and oxidize sulfide either to elemental sulfur or to sulfate. If oxygen is present, the reaction is quite rapid. 25 plus 3O, plus 2H, 0 to 200. Under anaerobic conditions, elemental sulfur can still sediments, fuels, soils and the sulfate produced then can be reused by the autotrophs. In anaerobic environments, such as bottom of certain lakes, it is impossible to oxidize sulfide by this means, because the process of oxidation requires oxygen. But if infrared radiation is present in these environments, there are photosynthetic bacteria that can use it to manufacture carbohydrates and oxidize sulfide either to elemental sulfur or to sulfate. Elemental sulfur can also be utilized by other bacteria to form sulfate. If oxygen is present, the reaction is quite rapid. Under anaerobic conditions, elemental sulfur can still be oxidized to sulfate by certain bacteria if nitrate is present. Under anaerobic 6NO, trademark plus 55. Additions, sulfate can also X animals in the phosphorus cycle, can combine with sulfide to form iron sulfides, all of which are highly insoluble. Fes. Some ferrous sulfide is contained in sedimentary rocks overlying coal deposits. Exposed to the air in deep and surface mining, the ferrous sulfide oxidizes and in the presence of water produces ferrous sulfate and sulfuric acid. In this manner sulfur in pyrite rocks, suddenly exposed to weathering by man, discharges heavy slugs of sulfur, sulfuric acid, ferric sulfate and ferrous hydroxide into aquatic ecosystems. These compounds destroy aquatic life and cause acidic water. E. Phosphorus cycle. Phosphorus cycle has no atmospheric phase. It occurs naturally in environment as phosphate PO4 or one of its analogs, HPO, or HPO, either is soluble. Inorganic phosphate ions, as soluble organic phosphate i.e., as a part of a soluble organic molecule, as particulate phosphate i.e., as part of an insoluble organic or inorganic molecules, or as mineral phosphate i.e., as part of a mineral grain is found in a rock or sediment. The ultimate source of phosphate in the ecosystem is crystalline rocks. As these are eroded and weathered, phosphate is made available to living organisms, generally as ionic phosphate. This is introduced into autotrophic plants through their roots, where it is incorporated into living tissues. From autotrophs, it is passed along the grazing food chain in the same fashion as nitrogen and sulfur, with excess phosphate being excreted in the feces. An extreme example of fecal phosphate is the tremendous guano deposits built up by birds on the desert west coast of South America. Phosphates can also be released as particulate matter from forest and grassland fires. In the detritus food chain, as large organic molecules containing phosphate are degraded, the phosphate is liberated as inorganic ionic phosphate. In this form it can be immediately taken up by autotrophs, or it can be incorporated into a sediment particle, either in the soil of a terrestrial ecosystem or in a sediment of an aquatic ecosystem. The sedimentary phase of phosphorus cycle remains comparatively slow. Then the organic phase. Besides phosphorus, there are biogeochemical cycles for all the other nutrients, minerals used by living organisms, as well as some that are not. Most of them has complete cycles in sedimentary phase. The availability depends on their solubility in water and availability of water as solvent. Thus, the geochemical cycles of different chemical substances are closed. The atoms are used over and over again. To keep the cycles going does not require new matter, but it does require energy. For the energy cycle is not a closed one. Further, the patterns of flow, both of energy and of chemical substances, are of great significance. The simpler pat. Wu. U. Input. Rain, dust output. Turns involve energy, as the sources of energy are external to the ecosystem, and flow is unidirectional through it. Chemical substances, on the other hand, are finite and have their origin inside the ecosystem, thus, they must continuously cycle within the system. Biogeochemical cycle of micronutrients. Many other micronutrients elements, such as calcium, potassium, sodium, etc., have a similar pathway of cycling like the other nutrients. They also involve the abiotic, soil, water, etc., and biotic phases, living organisms and their decomposition. These elements usually cycle within the same ecosystem and in small quantities globally. Usually, the rocks are the reserve pools and the weathering process enriches the soil and water with these elements. Though, the dust of these nutrients may be blown away by the wind and carried across ecosystems, and some of their amount is lost in the runoff to lakes and oceans and then to deep sediments. For example, in a tropical rainforest on average, more than 80% of total store of these micronutrients is found in the soil, with progressively less in vegetation, litter and the fauna, figure 10.9. Though, the concentration of trace elements tends to increase along the food chains in the sequence such as soil, plants, herbivores, carnivores and litter, detritivores. Thus, concentration of iron in a rainforest were 6 ppm in soil, 218 ppm in vegetation, 3054 ppm in herbivores and 3387 ppm in the carnivores. Many of these micronutrients become toxic to plants in high concentration. See Sharma, 1994. Aquatic ecosystems are the source of life on Earth. Aquatic ecosystems. Freshwater communities. The habitat approach describes the distinctive features of the major habitats and their subdivisions, how they are organized, the organisms present in each and the ecologic role of these organisms in that region, i.e., the identity of the major producers, consumers and decomposers. According to Elton, 1949, habitat is definable as an area possessing uniformity of physiography, vegetation, climate or any other quality the investigator assumes important. 4 major habitats can be distinguished: marine, estuarine, freshwater and terrestrial. No plant or animal is found in all 4 major habitats and, indeed, no animal or plant is found everywhere within any one of these. According to recent ecological trend, only 2 major habitats are more specifically ecosystems, namely aquatic ecosystems and terrestrial ecosystems, are recognized. Aquatic ecosystems. Liquid water covers about 3/4 of the Earth's surface either as oceans or as freshwater. Virtually all these waters contain life in one form or other, hence, aquatic ecosystems would be important for their sheer volume, if for nothing else. But aquatic ecosystems are historically the source of life on Earth. Even now, tiny single-celled marine plants are the main source of the Earth's oxygen supply, because most photosynthetic oxygen is derived from these plants. Clapham Jr., 1973. In addition, aquatic ecosystems are simpler in many ways than terrestrial ecosystems. The reason for this is that the omnipresent environmental factor which sets the tone for all aquatic systems, regardless of their biotic complexity, is water. It is the medium within which all aspects of the ecosystem coexist, both living and non-living. It is the source of all nutrients for aquatic life, including the gaseous nutrients such as oxygen and carbon dioxide. It is the medium by which organic and inorganic wastes and sediments are distributed throughout the ecosystem. The amount of light energy reaching the community is determined by the way in which light is absorbed by water. The heat properties of water determine much of the circulation patterns within the ecosystem and have a major control over the structure of the aquatic community that exists in any one place. Subdivisions of aquatic ecosystems. Global aquatic system fall into 2 broad classes definable by salinity, or amount of material dissolved in water, the freshwater ecosystems and saltwater ecosystems. The latter may include inland brackish water, as well as marine and estuarine habitats. In fact, estuary represents a transitional zone between a river and the sea, and it contains dissolved solid content intermediate between those of fresh and marine waters. Freshwater ecosystems, the study of which is known as limnology, are conveniently divided into 2 groups: lentic, standing or still water habitats, and lotic or running water habitats. Both can be considered on an environmental gradient. The lotic follows a gradient from springs to mountain brooks to streams to rivers. The lentic involves a gradient from lakes to ponds to bogs, swamps and marshes. Freshwater ECO systems, physico-chemical nature of freshwater. The freshwater of both kinds, lentic and lotic, has low percentage of dissolved salts and is subjected to the influence of a wide array of physical and chemical factors. The rise and fall of these factors very frequently affect the fauna, altering their number and diversity. Some of the important factors of freshwater environment are following. 1. Pressure, density and buoyancy. The pressure imposed on a lake-dwelling organism is the weight of the column of water above it plus the weight of the atmosphere. In all freshwater environments, maximum pressure is much less than in the ocean, and organisms appear to adjust to them readily. The absence of animal life from deep water is ordinarily a consequence of low oxygen supply, or low temperature, rather than pressure. The density of water varies inversely with temperature and directly with the concentration of dissolved substances. Water is most dense at approximately 4 degrees Celsius and becomes progressively less dense as it cooled below plus 4 degrees Celsius. Ice also expands markedly the colder it gets. It is because the coldest water is at the surface in winter that ice forms there, rather than at the bottom of a lake. In summer, the coldest waters of deep lakes are at the bottom. Dissolved salts increase the density of water. The density of most inland water bodies is much less than that of the ocean. However, when great evaporation occurs in a lake having no outlet, the lake may come to contain a higher percentage of salts, i.e., hypersalinity, than the ocean. The few species capable of living in these very salty lakes, e.g., Great Basin of USA, include some algae and protozoa, the brine shrimp Artemia gracilis and the immature stages of 2 brine flies, Aphyder gracilis and echians. According to the law of Archimedes, the buoyancy of an object is equal to the weight of the water it displaces. Buoyancy varies with the density of water, and is influenced by the factors that affect density. Viscosity, the measure of the internal friction of water, varies inversely with temperature and also influence buoyancy. Most aquatic organisms keep stations by swimming movements or have special adaptations to decrease the specific gravity of the body and take advantage of any turbulence in the water. For this purpose, freshwater aquatic organisms have some swimming adaptations, clinging organs in case of animal uploadic habitat, or following adaptations: absorption of large amounts of water to form jelly-like tissues, storage of gas or air bubbles within the body, formation of lightweight fat deposits within the body or oil droplets within the cell, increase of surface area in proportion to body mass, which increase frictional resistance. David, 1955. When an organism so equipped dies, the special mechanism quickly ceases to function, and it sinks to the bottom. 2. Temperature. The unique thermal properties of water are best demonstrated by freshwater environment. Diurnal and seasonal variations of temperatures are very much evident in these environments than in marine environments. A diurnal variation range of 4.8-5.0 degrees Celsius has been recorded by Srinivasan, 1964, in a tropical pond, with an average depth of 3.0 meters. In shallow water habitats, difference between day and night temperatures remain more conspicuous. For example, in a polluted moat with an average depth of 1.5 meters, the lowest nighttime temperature was 26.6 degrees Celsius, the highest daytime temperature was 32 degrees Celsius with a variation of 5.4 degrees Celsius. Srinivasan, 1964. However, the Kodaikanal Lake in South India showed a diurnal variation of only 2.8 degrees Celsius. Srinivasan, 1964. Flowing lotic waters of streams and rivers lack such wide fluctuations in temperature. Further, the lentic water of lakes and ponds undergo thermal stratification phenomenon according to the seasons. Thermal stratification has been reported most frequently in the lakes of tropical countries such as Java, Sumatra, etc. In fact, according to their temperature relations, lakes have been classified into 3 types. 1. Tropical lakes in which surface temperatures are always maintained above 4 degrees Celsius. 2. Temperate lakes in which surface temperature vary above and below 4 degrees Celsius. And 3. Polar lakes in which surface temperatures never go above 4 degrees Celsius. The seasonally regulated thermal stratification of lentic habitats has a significant influence on their inhabitant biotic communities. Decreasing temperatures often cause a fall in metabolism, resulting in a lower rate of food consumption. The extremes of lower and higher temperature have lethal effects on the aquatic organisms. So fluctuations in temperature of aquatic media regulate the breeding periods, initiate hibernation, gonadial activation and a number of other biological phenomena such as thermally oriented migration, etc., of freshwater biota. On the basis of their ability to tolerate thermal variations, most freshwater organisms are stenothermic with a narrow range temperature tolerance, but some are euthermic with a wide range of temperature tolerance. For example, the stenothermic oligochaetes include stenominimothermal forms, narrow range of temperature, e.g., Eolosoma, Megascolex moriti, stenomaximothermal, e.g., Darolimosa, or stenoptimothermal forms, e.g., Branchiodrolus semperi and B. Menonite Sateramaya, 1966. 3. Light. Light influences freshwater ecosystems greatly. The freshwaters often have a lot of suspended material. While affording protection to the light-sensitive species, these substances more often obstruct the light that normally reaches the water. The degree of such obstruction of light influence the productivity of the freshwater ecosystems. A shallow lake receives light to its very bottom, resulting in an abundant growth of vegetation, both phytoplankton and rooted vascular plants. These plants in living or dead states form nice food for consumers of grazing food chain or organisms of detritus food chain, respectively. The running water contains little plant or animal plankton not due to the lack of sunlight but because of the action of the currents in washing it away. Further, light controls the orientation and changes in position of attached species and their nature of growth, and it also causes the diurnal migration of planktonic species of freshwater. 4. Oxygen. Chemically pure water is biologically uninhabitable, and all freshwaters contains an array of chemical substances. The oxygen, which is the most essential chemical component of life processes, remain dissolved in freshwaters. The aquatic environments which remain in close proximity with atmosphere contain an abundance of oxygen that reaches the water either by direct diffusion or by movements of water such as wave action or water circulation. Lotic, moving water of streams and rivers often have a high percentage of oxygen. Aquatic plants supply water with oxygen that is formed as a product of photosynthesis. Rooted vegetation of shallow water. Zones and floating phytoplankton of open waters also produce oxygen. The amount of photosynthetically produced oxygen remain high at warm temperatures and at greater light intensities. The oxygen level in a tropical pond exhibits diurnal variation. It remains at peak between 14.00 and 17.00 hours of day. Srinivasan, 1964. Oxygen contents of a fresh water body are depleted in numeroxygen. The most essential chemical component is dissolved in outsways, primarily oxygen-utilized fresh waters, in the respiration of organisms and decomposition of dead organisms in the aquatic environment. While photosynthesis remains restricted to the surface layer of water containing phytoplankton and exposed regions of rooted vascular plants, respiration and decomposition occur at all levels. In stagnant pools with a lot of decaying vegetation, oxygen content often reaches a stage of complete depletion. The reduction in dissolved oxygen is magnified by the release of many gases as end products of decomposition or by the mixing up of waters of low oxygen content reaching the habitat as an inflow. Aquatic animals, with very few exception, i.e., those that breathe air, utilize the oxygen dissolved in water. Certain freshwater inhabitants such as many anaerobic bacteria and insect larvae of chironomids perform anaerobiosis and requires no oxygen. 5. Carbon dioxide. Aquatic vegetation and phytoplankton require carbon dioxide for photosynthetic activity. The carbon dioxide of freshwater environments is produced as the end product of respiration and of decomposition. Carbon dioxide also diffuses directly from the atmosphere and is readily dissolved in water to result in carbonic acid HCO, which affects the pH of water. It is also present in the freshwater as carbonates and bicarbonate of calcium, magnesium and other minerals. The growing plants and lime deposition bacteria and other animals may cause a depletion in carbon dioxide resources. Photosynthesis is the major cause for its strain. The high saturation levels of O and Colorado have been found to have toxic effects on aquatic biota. 6. Other gases. Streams and lakes contaminated by sewage and stagnant pools with decaying vegetation show an abundance of the gas, hydrogen sulfide, which is a decomposition product. This gas is highly toxic to living organisms and results into complete denudation of bottom fauna. Methane and carbon monoxide are other toxic gases which are the products of decomposition. Nitrogen, hydrogen, sulfur dioxide and ammonia are some of the other gases which are found dissolved in freshwaters. 7. Dissolved salts and salinity. Freshwater, being efficient solvent, contains many solutes in solution, but even then its salt contents remain under 1/5% than marine water, which contains about 35 parts per 1,000% dissolved salts. See Clapham Jr., 1973. Different dissolved salts reach the water by erosion, inflow and decay of aquatic forms. Dissolved substances have peculiar significance for floating aquatic vegetation and phytoplankton, since these organisms do not depend on the substratum for the supply of nutrients. Compounds of nitrogen, phosphorus and silicon are most important substances found dissolved in freshwater. Nitrate, nitrites and ammonium salts are essential for the food of aquatic vegetation such as algae and water weeds. Nitrate always remain available due to nitrogen cycle occurring between nitrogen-fixing bacteria and nitrogen-consuming plants. Ammonium salts in excess have a lethal effect on the fauna. Dissolved silicates of freshwater are readily utilized by diatoms and sponges in constructing their body structures such as shell in case of diatoms and spicules in case of sponges. All freshwater environments also contain small amounts of phosphorus which more often acts as a limiting factor. Utilization of phosphorus by plankton during the periods of abundance may result in a total elimination of other plants that require the element phosphorus. Many other elements such as calcium, magnesium, manganese, iron, sodium, potassium, sulfur, and zinc are found dissolved in water and influence the fauna variously. Iron being a growth-promoting element for salts water plants exists as a compound of oxygen. Ferrous oxide or sulfur ferrous sulfide RLRE. In different freshwater bodies, its influence fresh 1, IO. Ice often modified by the pH of water. Calcium HLETEDE is an essential element for plants. The K abundance and scarcity of carbonate of salts water hypotonic urine calcium determine the faunal composition. Equals. Deposition of calcium carbonate in water. Called marl is produced by the activity of _C. OL. Seawater plants. External cup.